So here, what we're doing is this. I'm just reminding you about permutations. Okay. Oh, sorry, wrong set of notes. Let me close that. So here I'm just reminding you about permutations. Okay. Remember, a permutation is really just a permutation of size r from n choices. It's just a list with r elements in it. And the list is formed, that is, elements are chosen without replacement, and order does matter. I mean, I'm not sure if I said the definition right exactly, but the whole point is order matters and you don't have repetition in it. Okay? And so how many possible such permutations can you make? That's what P of nr is. And the formula for it is n factorial over n minus r factorial. I did go over what factorials are last time. If though order does matter and you allow repetition, that's what I'm saying down here. So you're making the choices with replacement, but order still matters. Then the total number of possibilities, it's not a permutation, but the total number of possibilities will be n to the r in that case. So this is if, again, order matters, but you're making the choices with replacement. We did see an example like that last time. I think I mentioned also that n to the r stuff. I feel better saying it here as well. Okay. And again, it's really just the basic counting rule, which is why it's true. That's all it is. It's just the basic counting rule. That's all. Okay. We went through that before, the basic counting rule. Okay, so now what I want to go through is actually a famous problem called, it's solved, so we're not going to solve it or anything, but it's a famous problem called the birthday problem. The book does do it, but I think it's a really good thing to go through. So let's assume first that we have a room full of 3 people. And the experiment is we ask each person when their birthday is. We don't care about the year, when they're born, that is. We just want to know what month and day is their birthday. June 1st, May 8th, what else? October, 10th. Okay? And we're interested in the probability that all the birthdays are different. In other words, we want to know what is the probability that all 3 people have different birthdays. And just to keep it simple, we're assuming that the year has 365 days. In other words, we're assuming that the year is not a leap year. Usually in a leap year, if I remember correctly, I think what happens is there's 366 days. And I was going to say, we're not assuming that here. Okay, we're not assuming that here. All right, good. So basically, here, order will matter. Clearly we can't have repetition. Hopefully that's easy to see. But we want to make sure but order does matter here. And I'm trying to show you why through the slide. Mostly because if we ask the first person, okay? If we ask the first person, when their birthday is, okay? The second person's birthday has to be different. Has to be different. If the first person says, for instance, June 1st, then the second and third person, they would have to have birthdays different than June 1st. in order for all of them to have different birthdays. You know, person 2 could be a different day, like April 8th. And the third person has to have a birthday different than June 1st and April 8th. So that is what we're saying here. So basically, I know I wrote a lot here, but really what I'm trying to get you to see is that repetition is not, well, that's not allowed, and order does matter. Okay? All right. So anyway, since order matters and repetition is not allowed, you could probably guess that we're going to have to deal with a permutation. In other words, we want to know how many outcomes correspond to the event that the 3 people have different birthdays. We can figure that out using permutations. Permutations of those dates. You know, order matters and we can't have repetition. So the number of favorable outcomes here is this. Oh wait, let me get that laser thing going. Is this over here, as you can see. That's the number of favorable outcomes, as you can see. And now the experiment is asking each person their birthday. So the total number of possible outcomes, that is the size of our sample space, is this, 365 cubed. So the probability then that their birthdays are all different, right? The probability then would be this. Again, this is the number of favorable outcomes, right? No repetition and order matters. This is the sample space size, you know, how many possible outcomes there are. So for the probability, we just divide. And these numbers here, I didn't actually calculate by hand. I used the calculator, but we end up getting this probability, which is pretty high. So that's what we get in this case. This is not quite the birthday problem, but it's leading up to it. What I did do was I modified it down to 3 people, but let me just ask this first, though. Oh, sorry. Stop sharing. It's so annoying when I minimize it. Stop sharing. Let me do this. Just want to know if this makes sense or not. Does this make sense? You know, you could be honest. I really hope everyone understands, though. That's with 3 people. The question now is, okay, what about if we have more people in there? But the idea is still the same. It looks like people are saying they understand, which is a good thing. So let's do it. All right. Okay. Oh, wait. Oh, that's what I forgot to say. Sorry, I forgot to say it's about the quiz that you're going to have. It's not there yet. The questions will ask you to write your fraction in reduced form, you know, in lowest terms, that is. I know I didn't go over how to do that, but if you do need help with that, don't be afraid to ask me, okay? So I could definitely help you with that if necessary. Okay, I mean, it's really annoying because I was hoping that that would not be the case, in that the questions would not ask you to write your answer in lowest terms. Unfortunately, they do. I couldn't get around that. But again, if you need help doing that, don't be afraid to ask me. So that's something I forgot to say earlier. All right. Not to say you can't handle writing it in lowest terms, but, you know, don't be afraid to ask me for help is what I'm saying. All right, so this is for 3 people, right? You know, this is the probability of that all 3 people have different birthdays, right? So again, since order and repetition mattered, we had permutations. And that's what the P of 3653 was. The sample space, again, the experiment was asking each person their birthday. There's 3 people, so for each person, there's 365 possibilities. So the sample space we got from the basic counting rule. What about 5 people? Well, But for 5 people, the idea is similar. In that, again, we're assuming there's 365 days in a year, so it's not a leap year. Okay, so again, the experiment is asking each person their birthday. Okay, so that's what the experiment is. So in the sample space, there's 365 raised to the 5th possibilities. You know, from each person, each of the 5 people now, you're asking what their birthday is. And any day is a possible day. So we're just using the basic counting rule here. I was going to say that. Now we want to know how many outcomes are there where they all have different birthdays. So in other words, where there's no repetition, and order still matters. So again, we need permutations. So from here, our probability then will become this. The probability of 365, 5 divided by this. Okay? So this is what our probability will be. We have P of 365, 5 over 365 to the 5th. So because of that, so this is what our probability is, you know, the number of favorable outcomes divided by the total number of outcomes. And so this quotient is just equal to this. So it's pretty likely. Remember, the closer the probability is to 1, the more likely it is. Okay, let me just get the recording.